Hello and welcome to my presentation, Spaced Repetition and Mnemonics Enable Recall of Multiple Passwords. This paper was first presented at the 2015 Network and Distributed System Security Symposium in San Diego, California by Jeremiah Blocky, Saranga Komanduri, Lori Cranor, and Anupam Datta, all part of the Carnegie Mellon University Computer Science Department. In this paper, the authors present a method for formulating and memorizing multiple unique strong passwords called PAO stories. PAO stands for Person, Action, Object. The authors conducted a study wherein users memorized at least one brief one-sentence story involving at least one action and one object, and usually a famous person as well. In order to memorize several passwords, the user rehearsed inputting these action-object pairs from these stories following a prescribed schedule. Now for a little bit of background. Passwords are often secured with cryptographic hashes. If the password is common, though, an attacker can mount a dictionary attack by comparing the hash of the common password with other common hashes. There is a cost, however, associated with evaluating each hash. This table is based on research presented by Bono and Schechter at the 23rd Usenix Security Symposium. Here we see that for SHA-256 based hashes, the cost is very small. Iterated password hashing, along with scrypt and bcrypt, increases the cost by several orders of magnitude. But this is still below the threshold that hackers consider too expensive. But there are techniques to increase the cost further. If we up the number of cores to 1024 and oppose a 2-minute wait on the hash calculation, the cost rises over the threshold. Person, Action, Object, or PAO stories can be combined to make passwords that are very costly for hackers to discover. The total cost of cracking a single password multiplies the cost of evaluating a single hash with the number of possible words or phrases divided by 2. With the PAO technique, action-object pairs are randomly generated from the list of 92 actions and 92 objects. This yields 8,740 possible pairs for a password consisting of just one pair. As more pairs are added to the password, this number grows exponentially. As you can see, the cost of hacking a PAO password with just one action-object pair is mere pennies, even when the single hash evaluation cost is above the threshold. Similarly, hacking a 2-pair password is relatively affordable, but adding just one more pair, however, raises the cost above what is worthwhile for most hackers. With the PAO technique, users are encouraged to memorize multiple stories, typically 4, each containing an action-object pair to combine into multiple passwords. Each of these passwords shares 1 or 2 action or objects called secrets with other pairs. These passwords form a sharing set family. In definition 1 listed here, the first parameter represents the total number of secrets, including in the set family. The second parameter represents the number of secrets in each password, and the third parameter represents the maximum number of secrets any 2 passwords may share. Variable m represents the possible number of total passwords. Therefore, a sharing set family of 842 involves 8 unique secrets, with each password having 4 secrets, of which it may share at most 2 with any other password. This configuration yields 14 passwords represented in these curly braces. The first password contains the action and object from the first 2 stories, and the last password contains the pairs from the last 2 stories. Even if an attacker discovers one complete password, she must figure out another entire action-object pair in order to hack even one other password. As a demonstration of the power of this technique, a sharing set family of 43, 4, and 1 has 43 unique secrets, but each password may only share one secret with any other. This yields a whopping 110 unique passwords. For their study, the authors recruited volunteers from Amazon's Mechanical Turk framework through one of their school's websites. Volunteers were paid small amounts for the initial memorization phase and for rehearsals, regardless of whether they remembered their passwords. The participants learned their passwords either through mnemonic techniques or with plain text prompts. For the mnemonic technique, users were shown a randomly generated scene. They were then prompted to pick a famous person from a drop-down menu. A photo of the famous person would appear. These two pictures would now be the visual cues every time the person returned to rehearse logging in. The volunteer was then shown a randomly generated action-object pair. The user was not allowed to pick the action or object because many would be inclined to choose words commonly associated with the person, like lightsaber with Darth Vader. This would make the password easier for a hacker to guess based on the visual cues. The participant was then prompted to type into the first text box a one-sentence story about all four items in order of appearance. In this example, a possible story would be Darth Vader bribing a roach on the lily pad. Next, the user was asked to find photographs of the action and object, and then in the last four text boxes, write the action and object twice each. The entire process would then repeat 3 more times, with the user being shown a new scene, choosing a new person, and memorizing a new action and object each time. The participant thus learned 4 different stories and memorized 4 action-object pairs, or 8 words. For the text method, instead of being shown pictures, the user was prompted with an action and object in plain text. They would then write a one-sentence story in the first text box about a person of their choice performing the action on the object. Next, they would write the action and object twice, then repeat the entire process 3 times. Immediately following memorization, the user would complete their first rehearsal. For the mnemonic group, users were prompted with pictures of their scenes and famous persons that typed in the corresponding action-object pair. Like in the memorization phase, the process repeated 3 more times with the remaining pairs. The text group was expected to simply remember their action-object pairs with no prompt, although they could search for them within the site. Each participant was allowed 3 failed attempts, after which they would be asked to repeat the initial memorization. The users would then rehearse a number of times according to one of several schedules. After the first rehearsals, users would return at increasing intervals. This table shows some of these schedules. For example, the 24-hour by 2 schedule has a multiplier of 2 and a base of 1 day. This means that the first interval would be after 1 day, then thereafter the interval would double to 2 days in between, then 4, then 8, and so on. The 12 by 1.5 schedule, with a multiplier of 1.5 and base of 0.5 days, had its first rehearsal after half a day. The intervals were increased by 50% thereafter. This type of schedule was first proposed by Pimsleur in 1967 in the Modern Language Journal. It has been used by other researchers. In fact, these authors used this schedule formula in some of their other previous studies. There were several metrics involved in determining the success of the study, which metrics were measured at every rehearsal. Num remembered represented the number of people who remembered their passwords at the most recent rehearsal. Num survived was how many remembered at every rehearsal up to this point. Num returned was naturally how many people returned for each rehearsal. Incidentally, many volunteers dropped out. They were surveyed for their reasons. Of those who bothered to answer, none cited trepidation about forgetting their passwords. Therefore, low confidence didn't seem much of an interference in this study. Num's successful return measured how many people who had returned had also survived or remembered their password at every previous rehearsal. Num failed measured how many people failed at any point, including any who had dropped out. Estimated survival projected the probability of remembering one's password at the current rehearsal J based on the survival at the most recent rehearsal I. Pessimistic survival estimate was named such because in determining the chance of remembering one's password, it included people who had already dropped and would obviously not be represented as remembering their password. In this case, I represents the current rehearsal. These graphs show projections of success at each rehearsal. They are nearly identical, with the pessimistic survival graph lines dipping only slightly lower, if at all, than the lines of the estimated survival graphs. For the pink and green lines, the underscore 1 or 2 means that the volunteers only had to memorize 1 or 2 stories, respectively. Understandably, the pink line stays high, meaning one story was easy to remember. Otherwise, we can see that the 24-hour schedules had the lowest survival rates. Also of note is that +2 start means that users were given 2 extra rehearsals on the day of memorization. When comparing the red and blue lines, we see that adding 2 rehearsals helped in the beginning, since the red line dips much lower at first than the blue line. But ultimately, both lines end at nearly the same percentage value, indicating that the extra rehearsals ultimately had little effect on long-term retention. The actual observed results yielded graphs very similar to the first two, meaning that the surveyors had a sound formula for predicting survival at each point of the study for each schedule. Note that for all of these graphs, only one title begins with a T, meaning only one group was given text prompts instead of mnemonic prompts. This table is another representation of the same results. It shows first how many people had returned and not yet failed. It then shows the probability of surviving each rehearsal. The confidence interval is shown last. Like in the previous graphs, we can see that the 24-hour rehearsals, aside from those only involving 1 or 2 stories, have the lowest drop in chance of survival. Interestingly, the text-based group has no lower survival rates than the other 24-hour rehearsal groups involving more than 2 stories, at least by the end. In fact, survival was ultimately better in the text-based group with 2 extra rehearsals than the mnemonic group with a similar schedule, although the text-based group performed worse at earlier rehearsals. Besides the group with only 1 story to memorize, the group with the shortest rehearsal intervals had the best chance of success. Also interesting is that for every group, the num successful returned has the largest drop-off between the initial phase and the first rehearsal. This could mean that the highest number of volunteers failed at the first rehearsal. However, most of the survival percentages are high at that first rehearsal. Therefore, the drop-off means participants were most likely to drop out after the initial phase. Again, upon surveying those who dropped out, the researchers found that nobody dropped due to low confidence. Rather, they were too busy or uninterested in continuing. The authors also performed a statistical analysis using the Cox regression model. The beta symbol is the regression coefficient measuring the success of certain schedules compared with a baseline schedule. In Table 5, the baseline is the mnemonic 24-hour schedule with doubling intervals. A coefficient of less than 1 means that the schedules listed performed better than the baseline schedule. As you can see, the expected coefficient value is also less than 1, meaning that the studies performed as expected. Table 6, however, has an expected coefficient value of greater than 1, unlike the observed value. This indicates that the mnemonic group was expected to perform better than the text-based group with the same schedule, at least when there were 49 failure events. In fact, in this case, the mnemonic group performed worse. In Table 7, however, the expected and actual coefficient values are both above 1, although the expected is much higher. The difference between these two tables is that the number of failures is lower in Table 7. This perhaps shows that the mnemonic group possibly performed a bit better at earlier stages, but the text-based group ultimately won out. The benefit of using this model is that, unlike previous models, it factored out those who dropped out in determining failure rates. It also took into account the time of failure. Although these techniques proved effective in helping users memorize several secure passwords, there remain a few caveats. First of all, many sites require users to reset their passwords periodically. Since the user wants to keep a password she can remember, she may simply add a few characters to her existing one. This defeats the purpose of resetting passwords, which is to throw off attackers who may have decoded the old password. The authors encourage these sites to have users strengthen their new passwords instead of simply choosing new ones, with action object pairs and employing one of the rehearsal schedules in order to memorize the modified password. The authors, however, don't address passwords that require numeric and/or special characters. But perhaps in these cases, similar-looking numeric characters could replace alpha characters within the action object pairs. Another obstacle is the interference the authors encountered in their study, particularly password sets became significantly more difficult to memorize when they involved more than one action object pair. The authors suggest that users mitigate this by staggering memorization. Start one story and rehearsal schedule at a time. Then, a week later, perhaps add another story with its own new memorization schedule. From this study, we've learned that action-object pairs, especially as part of concise stories, are an effective way to form several unique passwords. Memorization is manageable, especially with short interval rehearsal schedules and by tackling one story at a time. Mnemonic versus text-based learning proved to have little effect on long-term retention. Also, low confidence was not a factor for those who decided to drop the study. Therefore, users should not feel trepidation about using this technique in the real world. PAO stories can certainly aid in password formation for those employed in industrial control systems, especially when they have multiple accounts in different zones or with different permissions. Thank you for your time, and I hope you found this enlightening.